We begin with the trace. We add our magic decoders, which look at a very small amount of the trace, and then we get the vector of Hamming weights. And then we feed it to another magical device, which I showed you in the last 2 minutes of the course. Last week was it's an equation solver or some kind of algebraic setup, or some kind of brute forcing setup if you're really convinced of your computing power and you feel really close. And out comes the key. Could come out immediately, could come out in a day or a week. If you need to try a lot of possible Hamming weights. Maybe you got it wrong, so you're trying to move them a little. As I said, these measurements have noise. So, do I have 16 times 40 Hamming weights? I have actually more than that, because mixed columns is not an 8-bit operation. So we went over this last week. To do mixed columns, you need to do 11 elementary operations per column. So a column is 4 bytes. You need to do 11 operations, I think 11 or 13, to get these 4 bytes into a mixed column. So you have a lot of Hamming weights. We have a lot of Hamming weights. It can help you recover the key, right? Yes, or else you're correct. We replace the bytes of the Hamming weights to the bytes of the state to the Hamming weights of the bytes of the state, but the sizes stay the same. Yes. So to do this, we had to do a really intensive reverse engineering process for the device under test. We had to figure out its exact source code in the assembly language level, right? We needed to understand exactly what it's running, because we were actually trying to understand assembly language instructions. And we also had to build this army of decoders, hundreds of decoders, which receive as input the trace and output the Hamming. So we did a lot of profiling, what is called in the language of side channel attacks, or supervised learning in the language of the machine learning. Okay, so now we were only, how many traces did we use to do this template attack? I'm talking about okay, how many traces did we use? The answer is divided into 2. So we had what is called a profiling phase, an offline phase. This is hard in training. And then we had an online phase, which is easy in backup. So in the offline phase, when we were profiling, we used a ton of traces. But we didn't have the key. So we have a device which is completely exposed to us, but it doesn't have the key. We're after the key. We're following Kirchhoff's principle. We have a copy of the device in our lab, and we run a lot of things on it. This is the offline phase, and then we build this kind of model of understanding the device. And then in the online phase, when we encounter this device with the unknown key, how many traces do we get? 1, a few. Okay, we only get a small amount of traces. But what do we get? What is the size of this trace? This trace is not a scalar. This trace is a huge vector. It has hundreds of thousands of points, millions of points. Depends on the memory you have in your lab setup. Depends on your funding. It's a huge vector. So what does my data structure look like when I'm doing simple power analysis, when I'm doing template attack? I have actually only one trace. So I have the plaintext associated with this trace. And I have this trace, but this trace is not of size 1. If we look at the timing attack, we have a trace of size 1. When we look at this template attack, our trace is millions of points long. Okay, so our data structure is going to look a little different. In the timing attack, we had a lot of measurements with small traces. And here we have one measurement with a very large trace. So now, let's motivate ourselves. We found a few motivations of where can we do timing attacks. So when can we do template attacks? When is a good motivation that we can do that? Okay. If we have access to the device, if we have the device in our possessions, like a SIM card, a smart card, a pay TV card, a phone, copy protected video, stuff like that, then that's a natural situation. We can do timing attacks and template attacks. So can anybody think of kind of a sneaky situation where we can do template attacks even though we're not sitting at home or in the lab with our device? So there's one very interesting situation, a very funny setup or unique setup, and that setup is electronic voting. So in electronic voting, you go into the voting booth, you're alone for a few minutes or a few seconds. Nobody is allowed to observe you because voting, right? But you can't really spend a lot of time there. You can't spend an hour there. You can maybe, so you can bring your I don't know, your portable lab setup to the voting booth and plug into the machine and do that. So you can do it for a very short period. You can do it maybe once or twice. Another example I gave you last week, this nice movie with Sal Drimel and Stephen Murdoch. We're going to actually cyber a point of sale terminal. So you're inserting your card into the point of sale terminal, and your card is actually a very sophisticated cyber security attack setup, and you're attacking. Again, you can do this once or twice. You can do this time. Okay. So to summarize, if we compare these two attack models, this one has small traces but a large amount, and it can be motivated, and you have some motivations where this can be done. And this one has one trace, but it's very, very long. And again, the attack model is different, and you can justify it in some situations. So you can only get one trace, but you can have a very, very detailed trace. Right? So until the end of this meeting, I want to talk about kind of a combination between these two attack models. What are you asking something? So in theory, could I tap the whole trace? So in high data complexity, so let me develop this a little bit, please. I'm going to take a new attack model, a new threat model, which combines the two properties of the timing attack and the template attack. So just as in the case of the timing attack, I'm going to collect many, many measurements. It's a high data complexity operation. I'm going to collect many measurements. But like the template attack, I'm going to collect very, very long traces. So I'm going to actually collect power traces of the device under test. So I'm going to do this many, 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 many times. And now if you look, just think about the data structure that the analyst has. The analyst has thousands of traces, or hundreds of thousands of traces. And each one of these traces is very, very long. It's the size of an output of an oscilloscope. So in conclusion, you need a nice server, which isn't so bad. You can do other things with the server as well. And another thing that you combine, so in the case of the template attack, we needed really, really intensive reverse engineering. So when you're doing high data complexity attacks, DPA and CPA, you don't need so much reverse engineering. So you get the advantage of the fact that you don't need so much reverse engineering. This is a good thing. You get another advantage that you can actually look in the middle of the computation, not in the end. So you can kind of isolate what's going on. So two advantages. What is a disadvantage? What is bad or wrong or weak about high data complexity power analysis? Yes, space. So you need an expensive computer. Okay. So you ask your boss, and your boss gives you an expensive computer. It takes a long time. Let me tell you the template attacks. You might have a single trace, but then you have to pre-process it for days and days. So speed, it's arguable. You need the data, right? How are you getting there? So if I need the data, what is this actually a vulnerability of high data complexity attacks? The vulnerability is that the attack model is different. So I need to tell a story, a convincing story that says, not only can I measure in high resolution, but I can measure thousands and thousands and thousands of times, right? So this, in fact, reduces to the, as far as I know, in 2020. Let's see what happens when I give this course next year. This reduces to having a device in my possession, right? I have the device in my possession. I need to cut it or probe it somehow or drill into it, and I need to leave it in my lab for weeks and weeks and weeks and then run this data measurement center. Maybe for a weekend, okay? For a patient, if you're Israelis, you do it over the weekend. But I need to justify to my systems engineer why this attack is a risk. And the risk is, as far as we know in 2020, it's only relevant to machines which are in our possession. There is a very, very experimental. So, remote, how do you do remote in this situation? Oh, if some okay. If somebody gets interested. So to do remote, you need some way of measuring the instantaneous power consumption of a remote system. And as I said, in 2020, I can't tell you about any way of doing it. There is some very, very experimental work that shows that if you have an FPGA connected, it's called capsule, FPGA connected to the same bus as a CPU, you can measure stuff like that. Let me just put the so there is, yeah, this is the paper. I'm going to put it in the chat. This is a very, very experimental work by two serious people in Cornell, but they're saying you can measure power consumption using an FPGA remotely. So now all you need to have is an ability to program an FPGA with software of your choice, with firmware of your choice, and this FPGA has to be on the same system and the same hardware as the device under test. So this is, as I said, it's very exciting as a researcher, but it might be less exciting to your systems architect. So right now,